All right, hello everyone. The end is near. We're getting there. So we have two more chapters we need to cover, calorimetry and the first law. And I thought about it, I'm just going to do them separately. It makes more sense to compartmentalize and do two videos. So this is a calorimetry video. The goal of this video and of this chapter in general is to help us become familiar with an energy that we've heard of and we've mentioned, but we've never quantified, which is heat. And so we've come across heat in the sense that we've said, oh yeah, well, if there's friction, block slides down the incline, it loses energy to heat, but we never really worried about heat because it wasn't part of mechanical energy. So we do want to give a definition of heat and kind of get a better understanding of how we might be able to quantify how much heat flows in or out of a system. And the reason is that we're going to need that in the first law of thermo to quantify then work done by the gas, heat transferred to the gas, and the net effect on the gas's internal energy. So we do need to basically make a pit stop and talk about heat and find formulas to quantify how much heat goes in or out. So that's the goal of today's video. Let's start with the definition of heat, because definitions are always nice. And heat is, first of all, it's an energy, and it's the energy transferred between a system and its environment because of a temperature difference between the two. So, simple example, if it's wintertime, the temperature in your house is higher typically than the temperature outside, hopefully, and there will be a tendency for the heat inside your house to want to leave and to flow out of the house. Now, there's plenty of ways by which you try to prevent that, of course. Dual pane windows, insulation, a lot of other ways. But the point is, while you're trying to trap heat, the tendency is that the heat will want to flow out because heat flows from the hot body to the cool body. That's the direction of flow of heat. And that being a definition, we can then try to wonder, well, what happens if we put in interaction two systems that have different temperatures? So maybe we have, I don't know, ice that we pull out of the freezer and we mix it with warm water in a thermos. And if we wait for equilibrium, what's our equilibrium temperature going to be? Right? Or you put a horseshoe in oil to cool it, what's the final temperature of the oil once the horseshoe has been cooled? That's basically what's the final temperature of both of them. So that's what we're going to try to do. That is calorimetry. There's much more to heat transfer than simply calorimetry, and by no means will we be experts, in fact, in either by the end of this video, but at least we'll have introduced the idea of calorimetry and the formulas that we're going to need for this chapter, so that when we see similar formulas in the case of the ideal gas, it doesn't seem like they just show up out of nowhere. So let's talk about what happens when we heat an ice cube, because there's a few things we need to agree on before we start writing formulas. Now let's say you go fetch an ice cube in the freezer, you put it in a pot on top of the stove, and then you cover the pot with a lid so that eventually you don't lose any vapor. You turn on the stove and you warm up the ice cube. Well, the ice cube's going to warm up, eventually it's going to melt, you're going to get liquid water, the liquid water will warm up, eventually will boil, and eventually will boil off entirely, leaving you with vapor trapped in the pot. And you could keep on going, for that matter. You could keep heating vapor, but there's no further phase change for the water molecules to undergo. Vapor will be their final phase in that sense. Of course, if you cool it, then you could condense it back to liquid water, but the point is, once you've reached the vapor phase, there's nowhere else to go if you keep heating. And as we do this process, at times the temperature of the ice cube is going to change. So of course it has to make it to 0 and then eventually to 100 to boil. But at times it will remain the same, and it's important to know when those things happen. So let's say that we have our ice cube that we got out of the freezer, and the initial temperature of the ice cube, just picking a number, is -5 degrees Celsius. Okay, fine. And you heat it on the stovetop, and its temperature will increase. But until the temperature reaches 0, there is no phase change. That's the melting point for water. And when the ice cube reaches 0 degrees, it will undergo a phase change. It will melt at constant temperature. The temperature of a pure compound remains constant during a phase change. So as the ice or the solid water turns into liquid water, the temperature of the water does not change. It stays equal to 0 degrees. But then, of course, once you have liquid water, then your liquid water will warm up and temperature will change again until you reach the boiling point, which is 100 degrees Celsius. And then the liquid water will turn into vapor at constant temperature, 100 degrees. And then, since you've trapped the vapor, then it could keep going as far as you might imagine. Certainly no further than the max temperature of the stove, but the point is you can keep heating it. There's nothing else that's going to happen other than the vapor is going to warm up. Okay, and with all of this, what we're seeing is that there are different regions here that seem to appear. Right? There's just different segments of this transformation that we need to point out. First of all, there's the phases. So this is going to be a solid phase. Here is going to be solid plus liquid. This is a phase change. Then this is all liquid. This is liquid plus gas, because you get a phase change. And then this is just gas. And past that point, you just remain gas. There's nothing else. Okay. And you could go in this direction, certainly, if you're heating the ice cube. You could imagine, perhaps, that you have very hot vapor and you're somehow pulling heat out of your system, cooling the whole thing. So you could also come back down like this, and you could freeze water vapor. It might take you a minute, but keep pulling heat out, and you cool it and condenses, and then it freezes. So you could go one way or the other. Now let's say we are doing what we were initially doing. In other words, we're increasing the temperature overall. This transformation is called fusion. And then once we make it up here, this transformation is called vaporization, going this way. But if you go the other way, then you get condensation. And then here, you're going to get freezing. Now, in each step of this process, heat is being transferred between the stove and the pot with the ice cube. So in every single step, there's heat transfer. In fact, there's always heat flowing in. But because temperature stays constant, does not mean that heat stops flowing in. That's not true. It just means that the temperature doesn't change as you undergo the phase change, but you still have heat coming in. And so there's, in effect, two different types of transformations we need to worry about. There's these transformations, which we might call warming or cooling if you go the other way, meaning that the temperature does change during these transformations. And then we have phase changes here and here, during which the temperature stays constant, which means that temperature probably plays a role in the former, but not in the latter, and we need specific formulas to describe each type of transformation. So let's come down here and introduce the idea of specific heat, and then we'll talk about latent heat. Okay. Now, what is specific heat? Specific heat is the amount of heat required to increase the temperature of 1 kilogram of substance by 1 degree Celsius, or for that matter 1 degree Kelvin, because the temperature change of 1 Celsius is also a temperature change of 1 Kelvin. Though typically we tend to use Celsius in this chapter, even though it's not the proper unit for temperature. Kelvin is the proper unit. So basically this is a quantity, specific heat, that is substance specific, right? And the amount of heat required to increase the temperature by 1 kilogram by 1 degree is typically called little c, the specific heat. And of course, the greater the specific heat, the more heat will be required to increase the temperature by 1 degree Celsius of 1 kilogram of substance. Okay. And we have a formula here where we can say that the heat required to change the temperature of a mass m of substance with specific heat C by delta T degrees is equal to Q is MC delta T, or often referred to as Q is MCAT. And delta T, of course, is T final minus T initial. Okay. Now, by the way, because it's T final minus T initial, if T final is greater than T initial, in other words, temperature went up, Q is positive. Makes sense? Q positive means you have to supply that amount of heat to bump the temperature up by that amount. But if TF final is less than T initial, temperature went down, then this is negative and Q is going to be negative, which means that that is the amount of heat that you must remove from the substance to drop the temperature by that amount. Okay? So this is something that is going to describe how much heat is needed to cause a certain change in temperature. In other words, it is something that applies to these segments of this transformation during which there is a temperature change. On the other hand, we have to have a formula or something to describe and quantify the heat exchanged during a phase change. Okay, now that brings us to latent heat. All right, now what is latent heat? This is the amount of heat, which is usually denoted by capital L, required to transform one kilogram of substance or compound from one phase to another. Now, this gets a little bit trickier because Q is equal to MC delta T is nice because it takes care of itself. In other words, if delta T is positive, Q is positive. If delta T is negative, Q is negative. I don't have to worry about the signs. The math takes care of it for me. When it comes to latent heat, that's not true. When it comes to latent heat, I have to decide what's going on, right? So I have a first phase change between the phases solid and liquid, Well, if I want fusion, which is going from solid to liquid, then Q fusion is going to be plus mass m of substance that I have multiplied by the energy per kilogram required to melt, in this case, that substance. But I have to remember that it's positive. I don't have to write plus, but the point is it's a positive number, but I'm responsible for the sign. In other words, if I were to go the other way, if I were to go from liquid to solid, I would have to freeze a mass m of substance. Well, that would still be an amount of heat ml, but I'd have to remove that heat in order to freeze it, so I need a minus. Now, by the way, it's quite remarkable that it's the same amount of energy in both directions. It's just a matter of whether it goes in or it goes out. Now, since we're going to have to worry about liquid-gas phase change as well, let's be a bit more specific here. Let's call this latent heat the latent heat of fusion, L fusion. But I have to pick the right formula depending on which phase change I have. Okay, similarly, between liquid and gas, or liquid and vapor, I'm going to have, well, if you're going to go from liquid to gas, you're going to boil, so Q boil is going to be the mass m of substance times L. It's going to be a positive amount of heat because I have to supply it. And this is going to be L vaporization. And then Q condensation is going to be minus m L vaporization. So there are formulas to quantify the heat exchanged either during a phase change, where temperature doesn't change, or during a heating or a cooling phase, where temperature does change. But heating and cooling is easy. Q is equal to mc delta T. The sign takes care of itself. However, for phase change, it is up to me to pick the right formula. Okay, so fairly straightforward. I mean, none of these formulas are complicated. It's just a matter of understanding how we incorporate them into problems. So let's do a couple problems just to get a hang of this thing. We're going to start with this one, which is also going to be about heating an ice cube. And we're told that we have an ice cube with a volume of 200 milliliters. We'll get to that problem later. It has an initial temperature of minus 10 degrees Celsius. It is heated up until it melts. Then the liquid water receives 35,000 joules of heat and reaches a final temperature T2. First question, what is the final temperature T2 and what is the final state of the water? And then how much heat does this transformation require overall? Okay, now first things first, when it comes to calorimetry, which is what this is, right? We heat exchange between substances and possibly at least warming and cooling, possibly also phase changes. We need to know what our final state is. Now we don't quite know, but our best guess is that since we know that we go all the way up to the point where the ice cube is fully melted, it's probably going to be liquid water. It could be vapor. It depends how much energy I need to go from liquid water at 0 degrees to vapor, and if 35,000 joules is enough. But my best guess, at least for now, is that it's going to be liquid water. It's certainly not going to be solid water. So, final state is going to be presumably liquid water, but to be confirmed. If we find T2 between 0 and 100 degrees, then we'll feel pretty good about that, fine. Okay, so then I have an ice cube with 200 milliliters, basically, of water, which means that I have to be able to figure out how much mass of substance I have, how much mass of water I have, because that's what I need to do the calc. And the, what am I trying to say here? To find the final temperature T2, I don't actually have to worry about warming up the ice to 0 and then melting it. That's kind of already a given. I only have to start thinking about the problem from 0 degrees liquid water onward and figure out 35,000 joules, where's that going to take me, right? So that's the final state. The initial state, now the initial state is up to me. You could argue, well, isn't it the ice cube at minus 10 degrees? Like, sure, if you want, but let's say we forget all about that because we know that we're going to make it to liquid water at 0 degrees anyway. Well, then let's choose to start thinking about the problem from that point onward. And let's say that our initial state is liquid water at 0 degrees Celsius. Okay. Now, how much water do we have? Mass of water. Okay. Now, the mass of water, by conservation of mass, is going to be equal to the mass of ice, which not that helpful because I don't know the mass of ice, I know the volume of ice. But it's okay because I know the mass density of ice as well, and I know that if I multiply my mass density here by volume, then I'm going to get mass, right? So that's going to be 920 multiplied by 200. Now this is milliliters. Okay, so milliliters is 10 to the negative 3. This is liters. I don't want liters, right? I want cubic meters is the right unit for volume because of this thing here. Okay, so 1 cubic meter is 1,000 liters. So this is going to be times 10 to the negative 3. All right. Now, real quick, what's that going to be equal to? It's going to be 920 times 200 times 10 to the power minus 6. That's going to be 0.184 kilograms of water. Okay. I'm doing this separately because it's the first time. Typically, I wouldn't even bother. I would just write everything in variables and solve, like I'm going to do now. But just so that we're clear, usually you do not. It's common, let's say, that to not be given directly the mass, but instead be given the mass density and the volume. So I'm not saying the problem couldn't tell you this off the bat. It could, but sometimes it chooses not to, in which case you typically have rho and volume. Okay. Now, the question is, how far is 35,000 joules going to take you? So let's figure out, let's assume that we received 35,000 joules and we're liquid water at 0 degrees. What temperature do we reach with those 35,000 joules? Okay, so the heat Q is equal to 35,000 joules will cause the liquid water to warm up to T2, which is going to satisfy the following formula. Now I'm going to solve for T2. I'm going to assume that we stay liquid water. I'm going to solve for T2, and I'm going to say that Q, the amount of heat, has to be mass of water, specific heat of water, T2, minus T initial. Okay? Just to be clear, T initial is 0 degrees C. And I'm going to solve for T2. As long as I get T2 less than 100 degrees, okay, everything's fine. Indeed, I remain in the liquid water phase. I only had to worry about warming the water up from 0 to T2. If I were to find, let's say, I don't know, T2 is 147 degrees, and be like, that doesn't work. That means that I move to the vapor phase at some point, and I have to rethink how Q is spent, right? I'm going to have to say it's going to warm to 100, then vaporize, then warm the vapor. So I'm making an assumption here that I remain in the liquid phase, and I'm going to see if that assumption is confirmed or validated by computing T2, and if T2 is less than 100 degrees, then I'm good. Okay, so what is T2 going to be? T2 is going to be Q divided by mass of water, specific heat of water, which is going to be Q divided by mass of ice, which is rho of ice, times V, times the specific heat of water. And of course, we already did the calc for rho ice V, but this is probably how I would do it. I wouldn't even do this. I would just directly go to this and solve, but yes, this thing here is the same as this thing here. So this is 35,000 divided by 920 times 200, 10 to negative 6, times the specific heat of water, which is given in 4,190 joules per kilogram per Celsius, or per Kelvin. And when we compute this, we get approximately 45.4 degrees Celsius. Okay, this is less than 100 degrees Celsius, so yes, we confirm that the final state is liquid water. So final state is liquid water. All right, so that's figuring out the temperature T2, and then how much heat does this transformation require? Okay, so this is the entire transformation. Right? I have to include going from ice at minus 10 degrees to 0, then melting at 0, and then warming up to T2 is 45.4 degrees. Okay, so there's 3 steps. There's step 1, which is warming the ice from minus 10 degrees C to 0 degrees C. Obviously, temperature changes during this transformation. How much heat is required? This requires the amount of heat Q0, let's call it. It's going to be mass of ice, specific heat of ice, times delta T. Well, mass of ice is rho ice times the volume of ice, as we've seen. Specific heat of ice is given. And then this is going to be 0 minus 10. Careful with your signs. And so this is going to be (920) times 210 to negative 6 times 2090 times 10. That's approximately 3,845 joules. Now that is simply to take the ice cube and to warm it to 0. I have not melted any of the ice into liquid water yet. So then I'm going to have to account for that. I'm going to have to account for melting the ice at constant temperature, 0 degrees. Well, that's a phase change, right? What phase change is it? It's fusion. And so it's a positive amount of heat, Q1, that is required, and Q1 is mass of ice times L fusion, which is going to be rho of ice times the volume V multiplied by L fusion. So that's 920, 210 to negative 6 cubic meters, and then L fusion is equal to 3.33
times 10 to the 5 joules per kilogram. And this is approximately equal to 61,272 joules.
Now, by the way, just as we're doing this, note that phase change is typically a lot more than just warming and cooling. Phase changes require an enormous amount of energy. Right? If you want to melt ice at 0 degrees, it is going to require a lot more energy than this. Right? So that's why, for instance, the space shuttle is covered in ceramic tiles so that when it re-enters the atmosphere, the friction against the atmosphere is going to heat up the shuttle quite a bit, but the ceramic tiles are going to absorb the heat as they just disintegrate and vaporize. Right? And we do that because one of the transformations that we know absorbs the most heat in physics is a phase change. Okay. So now we've taken our ice cube, we brought it to 0, we melted it at 0. The total amount of these two is going to be what takes me to 0 degrees liquid water. And then I know from before that I still need to incorporate 35,000 joules to make it to 45.4 degrees Celsius. Okay, so then there's warming the liquid water, which comes from the melted ice, from 0 degrees to 45.4 degrees. And I already know how much heat that requires. Q2 is 35,000 joules. I was told that off the bat. I don't have to compute it. I mean, I can. You can compute it if you want. You'd have to say this, right? You'd have to say it's mass of water, which, by the way, is the same thing as the mass of ice by conservation of mass. Seawater, and then 45.4 minus 0 will get you 35,000. Give or take some rounding, but pretty much 35,000 is what you're going to get. So what is the total heat? The total heat is Q total is Q0 plus Q1 plus Q2. That's 3,875 plus 61,272 plus 35,000. That is 100,117 joules. Right, that is the total heat required to go from ice at minus 10 degrees to liquid water at 45.4 degrees. All right. So the goal here was to kind of just manipulate these formulas and understand how you use them, right? But probably too simple to actually be an exam problem. Just a good appetizer, right? Now let's do a problem that was actually an exam problem, and let's go ahead and see how a typical calorimetry problem is structured and how you would go about solving it. Okay, so we have water vapor, 5 grams of it at 120 degrees Celsius, that gets bubbled into the bottom of a container of water that holds a mass. M water is 100 grams at a temperature of 20 degrees Celsius. And we are told that no water vapor leaves the top of the water. And if that's the case, we would like to figure out what is the final temperature of the water. Okay? So let's just talk about what happens here. You have a big container here that holds water. And you are going to bubble vapor that is above 100 degrees, at 120 degrees, into this container of water. But no vapor is going to leave the surface here. In other words, yes, it's vapor and the bubbles will likely tend to rise, but as they rise, they cool because they're in a lot of water. And they cool so much that they condense back to liquid, thus meaning that no water vapor leaves the top of the water. And so the question is, well, what's my final state? Well, my final state's got to be liquid water, right? All the vapor condensed.
And so this is not going to freeze, obviously. What it could have done is maybe partially vaporized the liquid water, but here for sure, my final state is going to be liquid water at, I suppose, temperature T is what they call it. I don't like that. I'm going to call that T final, at temperature T final.
Right. So a few things have to happen. The water itself, which is at an initial temperature T water is 20 degrees C, is going to warm up because of the hot vapor that comes into it. In fact, it is going to, let's say it differently. The vapor as it cools is going to release heat into the water, which will absorb the heat, causing its temperature to rise. So the water is going to have to reach a temperature higher than 20. But of course, the vapor, which is initially at 120 degrees, is first going to have to cool to 0, condense at 0, it's a phase change, and then cool even further to T final. Right? So water vapor undergoes 3 different transformations to cool to T final. The liquid water only undergoes 1. It just has to warm up to T final. That's it. And the heat lost by the vapor in cooling will be gained by the water, which causes it to warm up. And so those two amounts of heat are going to be the same. Even simpler, we're going to add them together and we're going to get 0. The same idea as, you take $500 from your checking and you put them into savings. Okay, well, the checking is minus 500, saving is plus 500, right? It's just transferred money. You're not richer, you're not poorer. And if you add the two, you get 0. Well, it's the same idea here. If we add the heat lost by the vapor with the heat gained by the water, we're going to get 0. And we should be able to solve for T final. Okay, so I need to know the final state because I need to know where I have to take each substance. So in other words, I need to know that it's liquid water at temperature T final to say that what I have to do, one of the things I have to do is warm the liquid water from T water is equal to 20 degrees to T final. Okay, now that is going to require an amount of heat, Q1, is equal to, well, it's just MC delta T, right? We're just warming, no phase change. So it's mass of water, specific heat of water, times delta T. That's going to be mass of water, specific heat of water, delta T is T final, minus T water, which is known. Now you could plug in values now if you want, and just leave T final as T final because it's your unknown. I don't recommend it, but you could. I mean, you could plug in this and just get an expression that's solely a function of T final if you want. But I'm going to leave it like this. Okay. So I have to warm the liquid water to T final. That is the heat required. So this requires heat Q1 equal to this. Then I have to cool the vapor from T vapor is equal to 120 degrees to, I'm just going to give it a name, T1 is equal to 100 degrees. Condense vapor at
100 degrees, and then cool the liquid water from T1 is equal to 100 degrees to T final. I have to do all of this. And of course, these things are happening at the same time in the container, right? But it's easier to do the accounting separately and to track each substance separately, and then you add the heats up to 0. Okay. This requires removing an amount of heat, Q2, which is going to be equal to, okay, now first things first, I am going to have MC delta T to go from 120 to 100, right? So I'm going to have mass of vapor, specific heat of vapor, T final T1 minus the initial temperature T vapor. That's going to be a negative number. It's the amount of heat I have to remove to go from here to here. Then I have to condense vapor. Okay, so, well, that's a phase change. I have to put the minus sign, and the amount of heat that I have to remove is mass vapor, L vapor. Now I have liquid water at 0 degrees. That's 100 degrees, excuse me. I have to drop its temperature to T final. This is going to be mass of water, specific heat of water. T final is my final temperature. I don't know what that is, but minus T1, which is 100 degrees. And by the way, mass of water here, don't get confused, it's not this guy, right? It's equal to mass of vapor, which is 5 grams, by conservation of mass. Okay, so very important to, again, this is why it's easier to track substances separately. The 5 grams of vapor become 5 grams of liquid water, right? So that's what that thing is. Okay, and that is the heat that must be removed. This is negative. This is obviously negative because of this. This will also be negative. That is all the heat that has to be lost by the vapor to reach liquid water at T final, our final state. And so then all we do is say that the heat lost from, lost by rather, the vapor is transferred to the liquid water, and because of it, Q1 plus Q2 is equal to 0. And that's, again, it's the same thing as transferring $500 from checking to saving. Minus 500 plus 500, if you add them up, it's 0, because you're not richer, you're not poorer, right? All the money that you took out of one of your accounts went into one of your accounts. So, same thing. So these two amounts, which were hopefully easy to track individually, can now be added up to 0, and we solve for whatever the unknown is. Okay, so what's Q1? Q1 is this. Okay, so it's going to be Q1 plus all of this I'm just going to go ahead here and change this to M vapor, right? Because that is 5 grams, all the same that this is 5 grams. Not to be confused with this is actually 100 grams of the liquid water at the beginning. Okay, all of this is equal to 0. Okay. And I am solving for T final. There we go. Where's T final? T final is here, and T final is here. So I have two terms that include T final. I have M water, C water, plus M vapor, C water, T final. And then the other terms are what? Now don't forget this guy. This is going to be minus M water, C water, T water, plus all of this, that stays the same. And then here I'm going to get minus MVCWT1. So minus MVCWT1 is equal to 0. Okay, so this thing here is going to be equal to, I'm going to throw everybody to the other side. So we're going to get mass of water, C water, T water, minus MVCV, T1 minus TV, plus MV LVAP, plus, getting tight, plus MV CW T1. And so finally, final temperature, T final, is going to be equal to all of this divided by all of this. Okay, so T final is going to be, mass of water is 100 grams, that's 0.1 kilograms. Specific heat of water is 4,000. It's a little more than that, in fact, but this is just rounded to make things easy. Temperature of water is 20, and doing everything in degrees. Mass of vapor is 0.05. Specific heat of vapor is 2,000. Do I believe that? 2,000? Is that true? Yes, 2,000. Times 100 minus 120 plus 0.05 multiplied by 2,000 kilojoules, so 10 to the 3, plus 0.05, specific heat of water 4,000, T1 20. No, T1 is 100, my bad, not 20, 100. Divided by mass of water, 0.1 times 4,000, plus 0.05 times specific heat of water, also 4,000, obviously. Okay, and you're going to find T final is approximately equal to 48.1 degrees C. It should be less than 100 because we have liquid water, so that makes sense. It should be more than 20 because, of course, the water is going to warm up. And 48.1, well, I don't necessarily know that that's correct, but it's not absurd. If it were more than 100 or less than 20, something is wrong. I got to go check my signs. But this seems reasonable-ish anyway. Okay, so the procedure is very much the same in all these types of problems where it ends up being a lot easier to do the accounting for the substances treated separately, where all that matters is what final state am I trying to reach and how many different transformations does that substance have to undergo to reach the final state. Well, the liquid water was already liquid, so it only had to go from 20 degrees to T final. So it only needed this amount of heat. The vapor had to cool, condense, cool some more. So there's 3 terms. That's the amount of heat that I had to lose. If I add it to Q1, I get 0. And then I can solve for whatever I want. It's usually T final, but you get an equation, and so you can solve for any unknown, right? The problem could have been phrased differently and could have said, if we want the temperature of the liquid water at the end to be 32 degrees Celsius, how much vapor would we have to bubble through, or something like that. You can solve for whatever quantity is in here, you can solve for it. But the point is, a lot of the time, what we want is the final temperature. So that's kind of the approach when it comes to calorimetry problems. It seems like a bit of a strange approach at first because obviously we know that everything's mixed together and everything's happening at the same time. But if you think of separating the two substances apart and just treating them separately to do the accounting, then it's actually very straightforward and very systematic how you solve a calorimetry problem. So definitely worth practicing because it's not uncommon to have calorimetry problems on the final. It tends to be the case that there's a little bit more
like if we look at probability, the probability of getting a first law of thermo type of problem is a little higher, but it's not 3 times higher, right? So calorimetry is worth spending time on because you can get really good at calorimetry really quick. Turns out you can get really good at the first law of thermo quickly, probably not as quickly, but the two kind of go hand in hand, and this is meant as an introduction to eventually thermo so that we can manipulate heat and understand the relationship between a temperature difference and heat transfer and so forth before we start doing that with ideal gases. Okay, so hopefully that made sense. We got one more video to do, so I'm going to try to post it as soon as possible. Should be before Dead Week. And like that, everything will be online for you to review if you want to use this material to review or just to get up to speed. So, you know, it'll come soon within the next few days, a first law of thermo video. But in the meantime, let me know if you have any questions. Best of luck for the final stretch. It's gonna be busy for the next 2.5 weeks, but after that, you get a break. So, you know, best of luck. Buckle down, and you know, do your best. It's a painful part of the year, but it's almost over. So, I will see you next time. Have a good rest of your week.